This is B. Naresh, working as assistant professor in AC department. And today's topic is problems on transistor connected to base biasing. So in this session, we are going to discuss some of the problems on connected to base biasing by using the bipolar junction transistor. So first, see the one problem. An NPN transistor, if the DC current gain, that is a beta, is 50, is used in common emitter circuit with VCC is 10 volts and RC is 2 kilo ohms. The bias is obtained by connecting 100 kilo ohms resistor from collector to base. Find the quotient point and stability factor. For this problem, we are going to choose a collector to base biasing by using the bipolar junction transistor. Hence, I considered as collector to base biasing with a bipolar junction transistor under the common emitter configuration. For this case, here I considered as NPN transistor, and in this NPN transistor, emitter is common for the input side as well as the output side. And based on the given problem, the DC current gain of this transistor means for this transistor, the current gain is represented as 50. Along with the biasing voltage, VCC, this is the positive biasing voltage. So in a problem, they mentioned that the biasing voltage is 10 volts. And the biasing collector resistance, RC, is represented as 2 kilo ohms. And the bias is obtained by connecting 100 kilo ohms resistor from the collector to base. So hence, this is the collector node. Collector to base, a resistor is a bias. The biasing resistance, it is called as the base resistance. And the base resistance value is 100 kilo ohms. And based on this biasing method, we need to find out the operating point and stability factor. So for this case, let us consider first, I given all the details, means what are the specifications are mentioned in the problem. The current gain of the transistor is a 50 and the biasing voltage, that is the VCC, is a 10 volts and the collector resistance is a 2 kilo ohms and the base resistance is 100 kilo ohms. For this case, I consider the same circuit collected to base bias. So if you want to identify the stability operating point, and we know that the operating point means Q is a functioning with respect to the VCE and IC in a common emitter configuration, where the VCE is the potential difference between collector and emitter voltage. Means we need to calculate this voltage along with the output current, that is collector current. So hence, we need to find out how much collector current is a flows and how much collector voltage is produces with respect to the common terminal, that is the emitter terminal. Hence, to define a Q point, we need to find out the collector current and the VCE voltage. To find out this collector current, and again from the collector current from the common emitter configuration, we know that the IC is represented as beta times of IB plus 1 plus beta times of ICBO, where the ICBO means the reverse saturation current when the collector base junction is open circuited. And let us consider this ICBO is much less than 1. The collector current is approximately equal to beta times of IB. So to determine this collector current, first we need to identify how much base current is the flows with respect to the biasing configuration, that is collector to base biasing. Hence, to identify this base current, first we need to apply the KVL rule at the input side. Means that input loop starts from this VCC towards collector resistance and towards the base through a biasing resistance, that is RB, and towards the base and emitter terminal, common terminal. Hence, from that, so if you want to write this loop equation from this VCC towards collector resistance towards the base and towards the lower potential. From this, we know that the VCC is equal to, and at this point, we know that and some IC plus IB of current is a flows across the collector resistance. Hence, the voltage drop across this collector resistance is represented as IC plus IB times of RC plus, and this node across this base resistance, the base current is a flows, hence it is represented as IB times of RB along with the potential difference between base and emitter is represented as VB. So if we expand this expression, so means this is VCC that is equal to IC times of RC plus IB times of RC plus IB times of RB plus VBE. So from this, VCC is equal to, this is ICRC. If IB is a common, RC plus RB plus this is VB. So from this relation, we are going to find out the how much base current is the flows. Hence, IB is represented as VCC, and you take this outside VBE and IC times of RC. Hence, VCC minus VBE minus IC times of RC by, and this IB term contains RC plus RB. Hence, that is divided with RC plus RB. And by using this one, just again you can, and here we doesn't know this IC. That is the reason we need to convert in terms of IB terms. Hence, again I'm cross multiplying these two terms. So IB times of RC plus RB, that is equal to VCC minus VBE minus IC times of RC. So, and from the transistor construction and from the common emitter configuration, we know that IC is approximately equal to beta times of IB. So why I'm going to convert in terms of IB means we have the two unknown parameters, IC and IB. So that is the reason to determine this base current, we need to convert this collector current in terms of base current. That is the reason. This IC is replaced with beta times of IB. Hence, IB times of RC plus RB, that is equal to VCC minus VBE minus IC is replaced with beta times of IB and its product with RC. So from this, now we need to calculate. So this, we take this outside. So means IB terms are the one side, IB times of RC plus RB plus this is beta times of IB plus RC, that is equal to VCC minus VB. So from this term, now I am going to calculate how much base current is the flows. So to determine this base current from this relation, so that is IB is equal to VCC minus VBE by, so in this term RC plus RB, and here the IB is a common, that is beta times of RC. So this is the expression in terms of biasing voltage and the biasing components, that is RC and RB. Now by using this mathematical relation of the base current, we need to find out how much base current is the flows in this case. Hence, let us consider the same circuit and these are the given specifications. Now I'm going to substitute in a IB relation. From the problem statement, VCC is the 10, but they are not mentioned that VBE. And based on this configuration, and to satisfy the amplifier condition, and we know that emitter base junction should be forward bias and the collector base junction is reverse bias. On the input side, this VBE means the emitter base junction becomes forward bias. And when that particular PN junction is a forward bias, and we know that the voltage drop across the forward bias diode is equal to cut-in voltage. Hence, from that representation, VBE is approximately equal to V gamma. Hence, you should consider that VBE is either 0.7 volts or 0.3 volts. That is 0.7 volts for silicon and 0.3 volts for germanium. That is your choice. In a problem, they are not mentioned the type of the transistor. So we need to assume the type of the transistor, means the transistor is made with either silicon or a germanium. If the transistor is made up with silicon, then let us consider the VBE voltage is 0.7. If the transistor is made up with germanium, we need to consider the VBE value is 0.3. So in this case, I consider the N transistor is made with silicon. Hence, the VBE parameter that is equal to 0.7. Hence, so VBE is 0.7 divided by collector resistance 2 kilo ohms, means 2 into 10 power 3 plus RB is 100 kilo ohms, hence 100 into 10 power 3 plus beta is 50 and RC is 2 kilo ohms, again 2 into 10 power 3. So now we can solve this one. 10 minus 0.7 divided by 2 into 10 power 3 plus 100 into 10 power 3 plus 50 times the 2 into 10 power 3. If you solve this ratio, then it gives that IB is equal to 46 microamperes, means that is 46 into 10 to the power of minus 6 amperes. So up to this point, we got the how much base current is the flows with respect to the biasing voltage and biasing components. To determine the operating point, we need to find out the collector current. Hence, we know that from the common emitter configuration, the collector current IC is represented as beta times of IB. So beta is in a problem, the beta is mentioned 50. And just now we got this IB value. What is IB value? 46 microamperes. Hence 46 into 10 to the power of minus 6 amperes. So then you can multiply this one, 50 into 46 into 10 to the power of minus 6. It gives the collector current IC is equal to 2.3 milliamps. So to define a Q point, so one parameter is collector current. Another parameter is we need to calculate the VCE voltage, means we need to calculate this VCE. To observe this VCE, so how to observe the VCE? VCE is related to the output side. Hence, apply the KVL at output loop. So based on this KVL principle, if you want to write the KVL loop equation at the output side, so we know that is VCC is equal to, so the current flows across this RC is IC plus I beta, means how to write this voltage drop across the RC. The voltage drop across the collector resistance is represented as IC plus IB times of RC along with the potential difference between collector and emitter, that is represented as VC, hence it is VC. So from this relation, based on this KVL loop equation, now we need to calculate how much collector voltage is produces with respect to the common terminal, that is emitter. Hence, so from this relation, I am going to find out the VCE. So what is the VCE? VCE is equal to VCC minus IC plus IB times of RC. If you observe this relation, VCC is a known parameter. IC and IB we observed. We got the values of IC and IB values. And RC is mentioned in our problem. Now we can substitute all these values to observe VCE parameter. So we got that IB is 46 microamperes and the collector current is 2.3 milliamps. Now we can substitute to identify this one. VCE is equal to VCC is a 10 minus IC is 2.3 milliamps, means 10 power minus 3 plus IB is 46 microamperes, means 46 into 10 to the power of minus 6 and RC is 2 kilo ohms, 2 into 10 power 3. Then you can solve this one. Then it produces VCE is equal to 5.308 volts. Now we need to define the operating point, means Q point we need to define. So the Q point is a functioning with respect to the VCE and IC. So if you want to define this Q point, the Q point values are means VCE Q and we need to write IC Q. What is the VCE value? 5.308, hence VCE Q becomes 5.308 volts ICQ means ICU, collector current is 2.3 milliamps. From that, the collector point Q point is 2.3 milliamperes. Then in the problem again, they're asking that to calculate the stability factor of collector to base bias. Hence, so we know that from the collector to base biasing configuration, the stability factor is defined as 1 plus beta by 1 plus beta times of RC by RC plus RB. So just can observe what are the values, what are the given parameters. Beta is a known parameter and RC and RB is also known parameters. Hence, we can substitute these parameters to observe how much stability factor is produces. So means 1 plus beta is a 50 by 1 plus this is 50 into RC means 2 kilo ohms, 2 into 10 power 3 by again RC means 2 into 10 power 3 plus RB is 100 kilo ohms means 100 into 10 power 3. Then if you solve this ratio, so means 1 plus 50 by 1 plus 50 times of collector resistance is 2 kilo ohms divided by collector resistance plus base resistance. If you solve this one, then the stability factor is equal to 25.75. Now we'll see another problem, the second problem. Calculate the quiescent current and voltage of a collector to base bias arrangement using the following the data. In that, the given specifications are VCC is the 12 volts and RB means the base resistance is 100 kilo ohms. Collector resistance that is RC is a 1 kilo ohm and the DC current again that is a beta is 100 and also specify a value of RB so that VCE equal to 7 volts. So in this problem, first based on the given specifications means with respect to this DC voltage 12 volts and the base resistance is 100 kilo ohms and the collector resistance is a 1 kilo ohm and the beta is 100. Due to these given specifications, first we need to find out the quiescent current and the voltage means we need to find out the operating point. So means we need to calculate ICQ and VCEQ. So these are the two parameters or relate the operating point. After that, and let us consider the VCE the 7 volts and with respect to this VCE 7 volts, how much base resistance is required. So due to this VCE parameter, we need to calculate how much base resistance is required. For this case, let us consider again the collector to base biasing configuration. So by using this configuration, now we need to calculate how much a collector current is flows and how much voltage drop is absorbed across the collector terminal with respect to the common terminal that is the emitter. So hence, so first again we need to calculate IC parameter. If you want to determine the IC from the common emitter configuration, we know that the IC is represented as beta times of IB. Hence, first we need to calculate how much base current is flows with respect to these biasing parameters. For this case, the given specifications are the DC current gain is from the problem statement. The given specifications are beta is 100, VCC is 12 volts, and the collector resistance is 1 kilo ohm, and the base resistance is 100 kilo ohms. Based on that, if you want to identify the base current, again we need to apply the KVL at the input side that starts from the VCC towards base towards lower potential through the emitter terminal. Hence, from that, so just now we observed that the base current, what is the base current we observed? IB is equal to VCC minus VBE minus IC times of RC by RC plus R. If you consider this relation, again in this relation, the two unknown parameters are there. One is IB, one is IC. These are the two unknown parameters. Hence, to solve the one unknown parameter, one should be represented in terms of another parameter. And from the common emitter configuration, we know that IC is equal to beta times of IB. Hence, I'm going to replace this IC is equal to beta times of IB. Further simplification. Hence, just simplify this cross multiplication IB times of RC plus RB, that is equal to VCC minus VBE minus, here IC is replaced with, this IC term is replaced with beta times of IB. Hence IC is replaced with beta times of IB into RC. Now take the common terms. So in this case, this is IB is a common, RC plus RB. Another IB term is beta times of IB into RC, that is equal to VCC minus V. So from this, we need to find out the IB current. So IB is equal to VCC minus VBE by, so RC plus RB in this beta times of RC. Now we need to calculate. So now we can substitute. Again, I consider that the type of the transistor is silicon. So hence the VBE parameter, that is equal to cut-in voltage. Why? Because of the emitter base junction is forward bias. Hence VBE I am going to assume as 0.7 volts. So based on the given problem statement, VCC is the 12 volts minus, and the VBE is the cut-in voltage, that is equal to 0.7, and divided by RC is a 1 kilo ohm, means 1 into 10 to the power of 3, plus RB is 100 kilo ohms, means 100 into 10 power 3, plus beta is 100, that is multiplied with the collector resistance. Collector resistance is 1 kilo ohm, means 1 into 10 power 3. If you solve this ratio, it gives that the base current is 56.2 microamperes. And by using this base current, now we are going to calculate how much current or collector current is flows in this collector to base biasing. Hence, we know that the IC is represented as beta times of IB. Hence, beta is, in a given problem, beta is 100, is multiplied with the base current. The base current is 56.2 microamperes into 10 to the power of minus 6. If you solve this product, then the collector current is 5.6 milliamps. So to define a operating point, again we need to identify the VCE parameter. Hence, I am going to calculate how much output voltage is produced with respect to the common terminal. To observe this VCE, again apply the KVL at the output side. If you want to write the KVL loop equation at the output side, we know that is VCC is equal to the voltage drop across this RC resistance is represented as I into R, means I means IC plus IB times of RC plus, and the potential difference between collector and emitter is VCE. So from this, we need to calculate how much potential difference between collector and emitter is produces. Hence, the VCE equal to VCC minus IC plus IB times of RC. Now you can substitute. The VCC is 12 volts minus IC is, we got just now, that is 5.6 milliamperes. Hence 5.6 into 10 power minus 3 plus IB is 56.2 microamperes. Micro means 10 power minus 6. That should be multiplied with RC, means RC value is 1K, 1 into 10 power 3. So if you solve this product, the VCE becomes 6.34 volts. So up to this point, we observe the collector current and the VCE parameter based on the collector to base bias. Now we need to find out the quotient current and the quotient voltage of collector to base biasing. So means that this quotient means it defines the operating point, the Q point. Hence, the operating point is represented as in terms of ICQ and VCEQ. We got this IC is a 5.6 milliamperes. Hence, the quotient point of the collector current is represented as 5.6 milliamperes, and the quotient point of the voltage at the output side, that is represented as VCEQ, that is equal to 6.3 volts. Then again in the problem, they are asking that to calculate the base resistance when the VCE is 7 volts. So up to this point, we observed that the VCE point is 6.3 volts. So in a given problem statement, the VC is a change from 6.3 volts to 7 volts. If the VC is a change from the 6.3 volts to 7 volts, and how much base resistance is required, that we need to find out. So further case, here I'm going to consider the VC is a 7 volts. Hence, again you can apply the KVL at this output side. So from this representation, so here I represented as, or otherwise we know that at the output side that VCC is equal to IC plus IB times of RC plus VC. So from this VCE is equal to, so why? Because of the, they mentioned the VCE and they mentioned the collector current is also there. Then we need to find out. So VCE is equal to VCC minus IC plus IB times of RC. So from this, I'm going to calculate this IC plus IB times of RC, that is equal to VCC minus VC. And from this, first we need to calculate how much base current is the flows. So let us consider here IC is replaced with beta times of IB plus IB times of RC, that is equal to VCC minus VC. If IB is the common term, so what happens, this is 1 plus beta times of RC into IB, that is equal to VCC minus VC. So in these two terms, if you take the IB is a common, if IB is a common, this is beta plus 1 times of RC, that is equal to VCC minus VC. From that, I am going to calculate IB. IB is equal to, from this relation, VCC minus VCE by 1 plus beta times of RC. So now we can substitute the given specifications. So VCC is the 12 volts, but we need to consider the VCE value is the 7 volts. Due to this VCE 7 volts, we need to calculate how much base resistance is required. So to identify the base resistance, so the base resistance is also depends upon the base current. That is the reason first I'm going to calculate this base current. So from the representation, VCC is the 12 volts, VC is mentioned as 7 volts divided by 1 plus beta is 100 and RC is 1 kilo ohm. So 1 kilo means 1000 or 1 into 10 power 3. If you solve this one, then the IB gives that 49.5 microamperes. So based on this specifications, 12 minus 7 divided by 1 plus 100 times of RC value, that the RC value is a 1 kilo ohm. If you solve this ratio, the base current is 49.5 microamperes. Now we need to calculate the how much base resistance is required to satisfy to produce the VCE is equal to 7 volts. For this case, apply the KVL at input side. So if you write the KVL at the input side, that VCC is equal to the voltage drop across this RC is represented as IC plus IB times of RC, along with the voltage drop across the base resistance is represented as IB times of RB, along with the potential difference between base and emitter is represented as a VB. So this is VB, that is equal to VCC. So from this, we need to find out the base resistance. Hence, so just expand the terms here. This is IC times of RC plus IB times of RC plus IB times of RP plus VBE, that is equal to VCC. So now I'm going to calculate this RB. So RB is equal to, so this is another voltage source. Take the outside, that is VCC minus VBE. Another two terms are, this is IC times of RC and this is IB times of RC, and just this is the one term IB RB. So from this I'm going to calculate RB. So hence it is divided with IB. But here again one unknown parameter is there, the collector current. So we need to find out how much collector current is flows with respect to the base current. So we observe that based on the VCE voltage 7 volts, we observe that the base current is 49.5 microamperes. And due to this 49.5 microamperes of the base current, we need to find out how much collector current is the flows. Hence, first I am going to find out how much collector current is the flows with respect to this base current. And we know that here IC is equal to beta times of IB. Hence, beta means 100 and IB is 49.5 microamperes means 10 to the power of minus 6. If you solve this one, the IC is 4.95 milliamps. Now we need to calculate how much base resistance is required to produce the VCE is 7 volts. For this case, I'm going to consider the same relation, RB relation. Now here I'm going to substitute. VCC is the 12, VB is 0.7 minus IC means with respect to this base current, we got this IC value is 4.95 milliamperes means 10 power minus 3. It is product with RC value. R is 1K along with minus IB value is IB times of RC means IB means 49.5 into 10 to the power of minus 6. That is multiplied with RC. RC means 1K, 1 into 10 power 3. That is divided with IB value is 49.5 into 10 to the power of minus 6. If you solve this one, RB gives that 127.2 kilo ohms. So that is the reason. With respect to the VC is 7 volts, the biasing resistance at the base is required as 127.2 kilo ohms. So, but in the problem statement, they given that RB is 100 kilo ohms. If RB is 100 kilo ohms, we observe that VCEQ is 6.34 volts. Whenever this VCE changes from 6.3 volts to 7 volts, we need to require the base resistance is, means the base resistance is changed from 100 kilo ohms to 127.2 kilo ohms. Now we'll see another problem. So, in the collector to base CE amplifier circuit of below figure, having VCC is the 10 volts, RC is the 2 kilo ohms, and the base current is 60 microamperes, beta is the 50, and VCEQ is 8 volts. Calculate the base resistance and stability factor. So for this case, the given figure is, so this is the given figure for this problem statement. If you observe this figure, the figure is again satisfies the collector to base biasing configuration of common emitter transistor or CE amplifier. So in this collector to base biasing, they are specifying that VCC is the 10 volts and the collector resistance is the 2 kilo ohms, and they mentioned that the base current. So base current is the 60 microamperes and the current gain of the transistor, that is under CE configuration, that current gain of the transistor is represented as 50 and the VCEQ operating point voltage is 8 volts. Now we need to determine the base resistance as well as the stability factor of this given state. So hence, so let us consider the given specifications and the given figure. For this case, we need to find out the base resistance. So means that base resistance, we need to calculate RB. Before going to this, first we need to identify that how much collector current is the flows. And from the common emitter configuration, we know that the collector current is represented as beta times of IB. Hence, beta is 50, they given that IB is 60 microamperes, 60 into 10 to the power of minus 6. Hence, the IC is represented as 3 milliamperes. Now we are going to calculate how much base resistance is required to produce the base current is 60 microamperes. For this case, let us consider apply the KVL at input side, means from the VCC to the collector resistance, towards the base, towards the emitter and towards the lower potential. So from this, if you want to write this KVL loop equation, we know that VCC is equal to the voltage drop across RC is IC plus IB times of RC plus the voltage drop across RB is represented as IB times of RB plus, and the potential difference between base and emitter is represented as VB. From this, we need to identify the base resistance. How much base resistance means we observe the collector current And in the problem, they mentioned the base resistance, collector resistance already there, VB we need to assume, and VCC is they are mentioned. So only the unknown parameter is RB parameter. So by using this relation, we are going to calculate how much base resistance is required to produce the base current, that is 60 microamperes. Now again, let us consider the transistor type is silicon, hence the VBE value that is equal to 0.7 volts. So from that, you can find out the ratio. From this, RB is represented as, by using this relation, the RB is represented as VCC minus VBE minus IC times of RC minus IB times of RC by IB. Now you can substitute the VCC is the 10 volts and the VBE we assume as a 0.7 minus IC. Just now we got that collector current is 3 milliamperes, means 3 into 10 to the power of minus 3. RC is a 2 kilo ohms, means 2 into 10 power 3 minus IB is a 60 microamperes and a collector resistance is 2 kilo ohms, means 2 into 10 power 3 divided by IB is 60 microamperes, 60 into 10 to the power of minus 6. If you solve this ratio, then it gives that RB is equal to 53 kilo ohms. Now again, in the problem, they're asking that to observe the stability factor. So now we need to calculate the stability factor in the collector to base bias. The stability factor is defined as 1 plus beta by 1 plus beta times of RC by RC plus RB. So for this case, just you can substitute the specifications. So 1 plus beta is 50 divided by 1 plus 50 times of RC means 2 kilo ohms, means 2 into 10 power 3 by, again RC means 2 kilo ohms plus RB we got that 53 kilo ohms, means 53 into 10 power 3. Then if you solve this ratio, the stability factor is equal to 18.09. Now similarly, we'll see the one more problem. An NPN transistor, if beta is 100, is used in common emitter circuit with a VCC is a 12 volts and RC is a 5 kilo ohms. The bias is obtained by connecting 50 kilo ohms resistor from the collector to base. For this case, we need to find out the quotient point and the stability factor. So based on the given problem statement, we know that the given biasing is collector to base biasing. And by using this collector to base biasing, we need to find out the operating point. Means, again, we know that the operating point is depends upon the quotient collector current and the quotient voltage, that is the VCE point. Hence, we need to find out how much collector current is the flows and how much voltage is the produces across the collector with respect to the common terminal, that is emitter. So first let us consider the given specifications, and now I'm going to first calculate how much base current is produces, and we know that from this collector to base biasing, the IB is represented as VCC minus VBE by RC plus RB plus beta times of RC. Now we can substitute in this case. So VCC is 12 volts, and again let the transistor type is BJT type is silicon. Hence, the VBE is approximately equal to cut-in voltage, that is 0.7. Hence, the VBE value is 0.7 divided by RC is 5 kilo ohms, 5 into 10 power 3. RB is 50 kilo ohms, 50 into 10 power 3 plus beta is 100 and RC is 5 kilo ohms. Just substitute the specifications, then solve this ratio. Now the IB is equal to 20.36 microamperes. So by using this base current, we need to find out the quotient collector current, means we need to find out the collector current IC. So we know that IC is equal to beta times of IB. So here the beta is 100, hence 100 it should be multiplied with the base current. The base current is 20.36 into 10 to the power of minus 6. If you solve this one, the IC current is, it gives a 2.03 milliamps. The collector current is 2.03 milliamps. So again, if you want to define the operating point, we need to find out the quotient voltage also. Hence, so up to this point, we observe the I base current as well as the collector current. From the given specification, we got that base current is 20.36 microamperes and the collector current is 2.03 milliamps. Now we need to find out the output voltage, means VCE. To observe this VCE parameter, apply the KVL at output side. So hence, from this output loop, we should write this VCC is equal to, so the voltage drop across this collector resistance is IC plus IB times of RC along with the potential difference between collector and emitter, that is represented as VC. From this relation, we need to find out the VCE. Hence, the VCE is equal to VCC minus IC plus IB times of RC. Now substitute the specifications. VCC is the 12 volts minus IC, we got the 2.03 milliamps, hence into 10 to the power of minus 3 plus IB is 20.36 microamps, means 20.36 into 10 to the power of minus 6. If you solve this one, then the VCE is 1.74 volts. VCE is equal to 1.74 volts. So up to this point, we observe the VCE parameter and the IC parameter. Hence, to define the quotient point, the Q point, so ICQ is 2.03 milliamperes and VCEQ is 1.74 volts. So these two parameters relate the operating point of the transistor amplifier. Now, again in the problem, they're asking the stability factor. So to observe the stability factor with respect to the collector to base biasing, we know that the stability factor is 1 plus beta by 1 plus beta times of RC by RC plus R. So now you can substitute the values. Beta 1 plus, this is 1 plus beta is 100 by 1 plus beta is 100 is multiplied with RC is 5 kilo ohms, means 5 into 10 power 3 by, again RC means 5 kilo ohms, plus RB is 50 kilo ohms, means 50 into 10 power 3. So if we solve this one, the stability factor is equal to 10. So based on the given problem statements, we observe that the operating point as well as the stability factor of the given collector to base biasing transistor amplifier. So up to this point in this session, we observed that some of the problems are related to collector to base biasing of common emitter amplifier. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.